We had enough practice. Yeah, question 18 is a summation calculation, right? What is the change in entropy for this reaction given the thermodynamic data below? And then, yeah, someone in the group me pointed out, well, isn't it already a delta S? That was just me um, typing this out. It's just the entropy value for that. It shouldn't have been a delta S. Right, so our entropy equals delta S of my products minus the reactants. So 4 moles of iron 2 chloride plus 3 moles of oxygen minus 6 moles of chlorine and 2 moles of iron 3 oxide. So plug in our values and all right, 118 joules, mole, Kelvin, 205 joules, mole, Kelvin, minus chlorine is 223. And 2 times 87 joules, mole, Kelvin. Right, we multiply by the molar coefficients and moles cancel out of all of these. And they just become joules per mole. All right, so 4 times 118 plus 3 times 205. I get 1087 joules per Kelvin minus 6 times 223 plus 2 times 87. 115, 12 joules per Kelvin, and I subtract, and I should get a negative 425 joules per Kelvin. Let me just try. Minus second. Yeah, I get a minus 425 joules per Kelvin. For that, for my entropy. So definitely be prepared to do a summation calculation. I was working on one of these with a student on Friday, and they literally just forgot to subtract, right? So just make sure you're doing the easy stuff, right? Multiply by the molar coefficients, and then just follow, right? Subtract when you're supposed to, add when you're supposed to, and especially pay attention to the sign because you might have to be subtracting like a negative, for example. So here we're going to do the same calculation for a delta H. All right, so my delta H equals the sum of my products minus the sum of the enthalpy of my reactants. This one's a little bit easier because a few of these are 0, which saves us a little bit of writing, right? So delta H equals 4 moles times minus 342 kilojoules per mole plus oxygen, got 3 oxygens at 0, minus 6 moles of chlorine at 0, and 2 moles of iron 3 oxide at minus 824 kilojoules per mole. Multiply by our molar coefficients again. Moles cancel out. All right, we can ignore the zeros. They're not going to change our calculation any. So 4 times minus 342. I get negative 1,368 kilojoules minus a negative, what's that, 1648? Yeah. Right, so here's where we're going to subtract a negative. And I think I get a delta H of something like 280. kilojoules, positive 280 kilojoules. All right, so again, the biggest mistakes people make is just the small stuff, right? Like this, like you're subtracting a negative, so we are adding this across. Correct. These equations, all summations, right? How do we find a change in anything? Change in anything is always final minus initial. So both of these equations, whether it's a delta S, a delta H, a delta G, right? They are always going to be the sum of, right, the entropy of my products minus the sum of how many moles and the entropy of my reactants. So we could plug in delta H, we could plug in delta G, right? Those summation calculations are always products minus the reactants. Let me just get rid of that. So yeah, 280 kilojoules for that. All right, oops, there was one more question below it, it looks like. Yeah, question 20, based on the delta H value determined in the previous question, how would you classify this reaction? So positive delta H is endothermic, right? And we know in general, endothermic is not favorable because it's absorbing energy from the universe. It's cooling the universe down. That decreases the entropy of the universe. So favorable or not, that comes from the sign on enthalpy on entropy, right? So we know not favorable would be a positive delta H, right? Endothermic, or a negative delta S because that decreases entropy. When we only have one, we can just say favorable or not, right? We need both. We need to put both together and calculate our Gibbs free energy to say, is this spontaneous or not? Right. On the flip side, favorable would be exothermic, right? That's releasing heat, that's warming the universe, right? And then also, right, would be a positive delta S that would increase our entropy. So we can only say favorable or not if we have one of them. If we put both of them together, then we can say this is spontaneous or not. All right, so question 21, based on the enthalpy and entropy values determined in the previous series of questions, what would the free energy be for this reaction in kilojoules at 25 degrees Celsius, right? So we'll put those together. We know delta G equals delta H minus T delta S. We need temperature in Kelvin, so 298 Kelvin. All right, delta G equals, my delta H was 280 kilojoules minus 290 Kelvin. And then my entropy was a minus 425 joules per Kelvin. So we can't plug that in right away. We have to do one unit conversion first. So we know 425 joules is 0.425 kilojoules per Kelvin. So this reaction, it's endothermic, results in a decrease in entropy, right? None of those things are favorable. This reaction is never happening as written because it's endothermic, because it decreases entropy. You put two unfavorable things together, this reaction is never spontaneous as written. We can still calculate the delta G, but it should be positive. All right, so 280 minus 298 minus 0.425. And yeah, I get a delta G of 406 kilojoules. So positive delta G, things are not looking good for this reaction, right? That reaction is non-spontaneous as written. And then I think I should have changed question 23, but people already started the exam. I didn't want to change it, but and then make it more confusing. But given the delta G value determining question 21, that should be 22. Or no, yeah, we did that in question 21. Under what conditions would this reaction be spontaneous? There are two answers, but yeah, I think the wording could have been better on my behalf, right? So number one, the reaction as is never going to be spontaneous because we calculated a positive delta G. So it doesn't matter the temperature. Temperature is not going to make it spontaneous, low or high. Pressure doesn't even show up in our equation. But because the reaction as written is never spontaneous, what that means is the reverse reaction will be spontaneous. So there were two answers there, and I think that's what led to the confusion because the way it's written, the way the question is written, I think most of you would probably just gravitate toward answer D, even though I was looking for two answers there. All right. Question 25. Then I get 15 minutes back my night. Speed. Yeah, given the following information, what is the melting point of phenol in degrees Celsius? So we know the melting point, you're at equilibrium between two phases, and we know you can find the equilibrium temperature. Temperature equals delta H divided by delta S, right? Because at equilibrium, delta G is 0. We can rearrange this equation to say, okay, what temperature does that switch occur? So my temperature equals my delta H is 11.514 kilojoules. I need to convert my entropy from joules to kilojoules. So we know there's 1,000 joules and 1 kilojoule. So this is 0.0366 kJ per Kelvin. So divide 0.03666 kilojoules per Kelvin. All right, kilojoules cancel out. Kelvin does not, because we're going to get a first temperature in Kelvin. So we divide. All right, 11.514 divided by 0.03666. And I get a temperature of like 314 Kelvin. All right. That is there, but we are looking for the temperature in degrees Celsius. So degrees Celsius equals all right, Kelvin minus 273. So 314 minus 273. All right, maybe the 41. Yeah. Yeah, we're looking at a temperature of 41 degrees Celsius. So that was the only trick there, is that we had to go through the temperature change, right? Because that original calculation is just going to give you temperature in Kelvin. We'll just convert it over to Celsius. All right. Any last questions?